So our concentration cell is not all that different from what we were looking at the Nernst equation for non-standard conditions. We're still under non-standard conditions. The difference here is that both our cathode and our anode are both the same element. In this case, we're looking at copper as our anode, copper as our cathode, and we have copper ions in solution. So under standard conditions, so when everything equals 1 molar, 1 atmosphere of pressure, we're going to see that we get no cell potential. There's no difference between them. However, if we create a solution where the concentrations are different in either side of the cell, we can get a small cell potential depending on the difference in concentration of those. Now our E naught of cell, the E standard cell potential, is still going to be 0 because we're looking at the exact same reaction. So all we're doing is relying on that Q value, that reaction quotient, to defect the cell potential from 0 to a little bit of something a little bit less than or greater than 0. Here we're looking at the same equation we were using earlier. We have E cell equals E naught of cell minus 0.0592 volts over N times the log of Q. And what we're going to see is that we use this the same way that we did for our other cell. Only now our E naught cell is going to be equal to 0 because our reduction and oxidation reaction are the same, so really the only thing we have to worry about is that second term. Now the value of N is going to be pretty easy to figure out because if I'm looking at the same process as the oxidation and the reduction, then my N is just going to be the number of electrons. There's really no balancing involved there. Now what we have to do is say, well, how do we figure out what Q is? Because how do we know what's the product and what's the reactant? Set up our reaction quotient. And what we see is that electrons flow from the lower ion concentration solution to the higher ion concentration solution. So when we set up Q, we say Q equals the concentration of the low over the concentration of the high. And you always can do that, low over high. So when you're setting up Q, use that, plug it into your equation, and then you can solve for E of the cell, knowing that your values are going to be pretty small because E naught of the cell is always going to be equal to 0. So what we see when we look at the electrochemical cell here is we see everything is the same as what it was before. We still have our anode and our cathode. We still have oxidation happening at the anode. We still have reduction happening at the cathode. We still have our salt bridge. We still have, in this case, our voltmeter, noting that we're under non-standard conditions. And this is a concentration cell, so we have to have a difference in the concentration between these two. It's not just enough that they're not equal to 1, but the concentrations in each half of the cell must be different from one another. When we look at what's happening at the anode, we see that copper ion is becoming oxidized to copper 2+ ion, so the solution becomes more concentrated with the flow of current, and on the other side the solution becomes less concentrated with the flow of current because we have copper ions coming out of solution, so we have the reduction happening there. And when we look at that reaction, what that results in is that the concentration on the low end is our product, and the concentration of the ion on the cathode side is our reactant. So that's where we get the concentration of low over high whenever we're setting up the Nernst equation for a concentration cell.